Imagine you are floating in space. No spacecraft, no suit, just you. And about 100 miles ahead of you is the most dangerous thing in the entire universe. A black hole. Now here's the question that has kept physicists up at night for over 100 years. And one that most science channels get completely wrong. What actually happens to you if you fall in? Do you get ripped apart instantly? Do you survive longer than you think? Does time literally stop? And most importantly, scientists just found something that changes everything we thought we knew. Stay with me because this answer is going to mess with your brain in the best possible way. First, let's make sure we're on the same page about what a black hole actually is, because most people picture it wrong. A black hole is not a giant vacuum cleaner sucking everything up. It is not a hole in space. It is actually an object, an incredibly dense object. So dense that its gravitational pull becomes strong enough to trap even light itself. The point of no return is called the event horizon. Cross that line and nothing, not information, not light, not you, comes back out. There are two main types of black holes we care about here. Stellar black holes form when massive stars collapse. These are relatively small, maybe 10 to 20 times the mass of our Sun, but only a few miles across. Then there are supermassive black holes sitting at the centers of galaxies. We're talking millions or even billions of times the mass of our Sun. The one at the center of our own Milky Way, it is called Sagittarius A star, 4 million solar masses. The type of black hole you fall into completely changes what happens to you, and most people don't know that. Let's start with the small one, the stellar black hole. You are approaching it. You are maybe 1,000 miles out. Here's where the first wild thing happens. Tidal forces. Gravity follows an inverse square law, meaning the closer you are to something, the stronger its gravitational pull. With a normal-sized black hole, the difference in gravitational pull between your head and your feet becomes catastrophic. If your feet are slightly closer to the black hole than your head, your feet experience dramatically stronger gravity. The result, you get stretched vertically and compressed horizontally. Physicists actually gave this a name. They called it spaghettification. That is a real scientific term. Look it up. You would literally be stretched into a long, thin strand of matter, like human spaghetti, before you even cross the event horizon. Now here is where it gets interesting. What if the black hole is supermassive, Sagittarius A star, or the one at the center of M87 galaxy, which we actually photographed in 2019? That image made headlines worldwide, a 6.5 billion solar mass black hole. With a black hole that large, the event horizon is enormous. We're talking tens of millions of miles across. And because the event horizon is so far from the singularity at the center, the tidal forces at the boundary are actually manageable. You could cross the event horizon of a supermassive black hole and feel nothing unusual. No alarm, no warning light, no physical sensation. You would cross the most significant boundary in the universe and have no idea it happened. That is not a metaphor. That is the actual physics. Now let's talk about time, because this is where Einstein comes in and where your brain is about to short circuit. Einstein's general theory of relativity tells us that gravity warps space-time. The stronger the gravity, the slower time moves. We've tested this. GPS satellites have to account for time dilation, or they'd give you wrong directions within minutes. It is not theoretical anymore. It is engineering. Near a black hole, this effect is extreme. Let's say your friend is watching you from a safe distance in a spacecraft. As you approach the event horizon, from their perspective, you slow down, you move slower and slower, your waving hand decelerates. Your voice stretches into a lower and lower pitch. Eventually, you appear to freeze right at the edge of the event horizon. Like a paused video, your friend never actually sees you fall in. They see you suspended at the edge forever, getting dimmer and dimmer as the light from you gets more and more stretched until you fade out entirely. From your perspective, you cross the horizon in normal time. You feel nothing unusual. You check your watch. Everything seems fine. Two completely different realities, both of them true simultaneously. That is what physicists call the black hole information paradox, and it is one of the biggest unsolved problems in physics. On say you are inside, if you somehow crossed without spaghettification, what do you see? This is wild. You would be able to see the entire future of the universe happening around you, because light from billions of years of future events would all be falling into the singularity alongside you, compressed into one blinding infinite display. You'd see stars being born and dying, galaxies colliding, all of it accelerated into the final moments of your fall. And that fall, for a stellar black hole, it lasts a fraction of a second. For a supermassive black hole, you could actually survive inside for hours, maybe longer, but the end is the same. The singularity, a point of infinite density, where our math, all of our beautiful equations, completely breaks down. General relativity fails. Quantum mechanics fails. We simply don't know what happens there. That is not a cop-out. That is the honest answer from the smartest people who have ever studied this. The singularity is where known physics ends. Now here is the part scientists just figured out, and why this video exists. For decades, Stephen Hawking proposed something called Hawking radiation. The idea black holes aren't actually permanent. Due to quantum effects near the event horizon, black holes slowly lose mass. They emit radiation incredibly faint, incredibly slow, but real. A stellar black hole might take 10 to the power of 67 years to evaporate. That is longer than the current age of the universe by a factor that doesn't have a name. But here is the problem Hawking himself identified. When a black hole evaporates, what happens to all the information about everything that ever fell in, you fell in. You were made of atoms, particles, quantum states. All of that information, by the laws of quantum mechanics, cannot be destroyed. It has to go somewhere. But if the black hole evaporates, where does it go? This became known as the black hole information paradox. And it has been one of the most heated debates in theoretical physics for 50 years. In 2023 and 2024, a series of papers, including work building on research from physicists like Geoffrey Pennington and Ahmed Almhiri, proposed something extraordinary. The information doesn't get destroyed, it gets encoded. In the Hawking radiation itself, the radiation that leaks out of the black hole over billions of years carries subtly in quantum correlations all of the information about everything that ever fell in, like a cosmic hard drive backup, scrambled almost beyond recognition, but theoretically recoverable. This points toward a resolution of the paradox using something called the page curve, a mathematical prediction for how information escapes over a black hole's lifetime. And the framework that makes this work, the holographic principle, the idea that everything happening in the volume of the black hole is somehow encoded on its two-dimensional surface, the event horizon like information on the surface of a hologram. If you fell in, you would eventually, over an incomprehensibly long time, be re-emitted as scrambled quantum information in the Hawking radiation. You wouldn't survive, but in some quantum sense, you wouldn't be erased either. Let's bring this back to the original question with everything we know. What actually happens if you fall into a black hole, if it is a stellar black hole? You get spaghettified before you even reach the event horizon. It is fast. It is final. If it is a supermassive black hole, you cross the event horizon without knowing it. Time runs differently for you versus any outside observer. You survive inside for some time, watching the compressed future of the universe. Eventually, you reach the singularity. Our physics breaks down. What happens next? We genuinely don't know. From outside, you appear frozen at the edge, fading out over billions of years. Your information, the quantum blueprint of everything you are, gets encrypted into Hawking radiation and slowly, across timescales longer than the universe's current age, leaks back out. Not you, not your memories, your face, your personality, but the quantum information that makes up your physical existence. That survives in the most abstract, most fundamental sense possible. A black hole cannot fully delete you. Here is what I want you to sit with. We live in a universe where the most destructive objects that exist, objects so extreme they break mathematics itself, are also apparently the universe's most sophisticated information storage systems. That is not poetry, that is physics. Black holes have been telling us something about the deepest nature of reality, about the relationship between gravity, quantum mechanics, space, time, and information. And we are just now, in the last few years, starting to hear what they're saying. The next big breakthrough, it'll probably come from combining general relativity and quantum mechanics into one unified theory. Something physicists call quantum gravity. We don't have it yet, but the black hole information paradox is pointing directly at it. When we solve it, and it will be the biggest scientific achievement in human history. And it started with a simple question. What happens if you fall in, if this video rewired how you think about space, time, or reality? Hit that subscribe button, because that is literally what this channel exists to do. Brain twist. Every week we take the questions that sound simple and follow them until your brain hurts in the best possible way. Next video, we're going somewhere equally extreme. You are not ready. See you there.